So static equilibrium of a crank slider. So back when you took statics, you probably thought it was really hard at the time, but now looking back on it in hindsight, it might kind of feel like the good old days compared to what you're being asked to do now. So good news for static equilibrium problems in a machinery class is that the statics hasn't changed. You're still just going to be doing sum of forces in the x and y directions, and a sum of moments is equal to 0. The downside is that you will have to do a little bit of extra work to do posture analysis to find all the right dimensions that you're going to use for your moment equations. So I've got 3 links in this problem, plus the ground link, so I don't really have to do a free body diagram for link 4 for the block, but I'll draw it just to kind of prove it to you that we don't need it. So without any dimensions for link 4, this isn't really a rigid body, it's really just a particle. So we're gonna have all forces kind of pointed right through the middle. So the 100 pounds is pushing from the right. F4 will be the force from the ground pushing straight upwards, and FC I'll put as kind of a diagonal force that just has to cancel out those other two. So really FC is just going to be 100 in the x direction and negative F4 in the y direction. And that's why I said you don't even really need to draw this link if you didn't want to. You could really just put the 100 and the F4, just apply those directly to link 3. But one reason to draw this if you want to is that we can make an assumption for this problem that there's no friction on link 4, because of course this would be a little bit different if there were friction between the link and the ground. Without any information provided about that, we'll assume that that's 0. Went down. So we're abandoned by your TA Indy. Once the going gets rough, he gets going. But it's not rough yet, so we've just got the 100 pounds and the 50 pounds. These are the externally applied forces. Fy, which is over at point C, the vertical force there. And over at point A, there's a pin joint, so I'll add an x and y component force over there at point A. Might as well do the easy parts first. Sum of forces in the x direction equals 0. Fax pointing right, 100 pounds pointing left. Fax equals 100 pounds. If only they were all this easy. Unfortunately, they're not though, because in the sum of forces in the y direction, we're going to have 2 unknowns, F4 and Fay. And if we want to sum moments, we can sum moments about point A. That will cancel out Fay and let us solve for F4, but I don't have any distances yet on this free body diagram, so that's actually a pretty big oversight. So free body diagrams for a rigid body, you absolutely have to have distances, because how else are you going to calculate your moment? So I'll write out the equation to figure out which distances we need. Sum of moments equals 0. I'm going to call this counterclockwise direction positive. So 50 times bx will be positive, plus F4 times cx is positive, minus 100 times cy will be negative because it's going to be rotating in the opposite direction. So in order to find F4, I'm going to have to find those 3 distances first. Oh, and looking back at this drawing, it's really not immediately obvious how I'm going to find these horizontal distances. So the distance from O2 to C and the distance from O2 to B. Now what I do have though are some diagonal lines. So 14 is a diagonal line that goes from A to C, and any diagonal line is the hypotenuse of a right triangle. So I'm going to start off my drawing by drawing a right triangle, this orange triangle that has 14 as its hypotenuse and also has 3 as its vertical side. And that's going to let me find CX is what I'll call it, the horizontal distance all the way across from O2 to C, just using Pythagorean theorem. If 3 squared plus CX squared is 14 squared, I can rearrange that, solve for C, 13.67 inches horizontally. And boom, that's one of the 3 done. Now I'd love to do that same thing for the other triangle, the one that has 7 as a hypotenuse, because, right then, but I don't know the angles, right? And I don't know the vertical length. That height 3 only goes to O2, but point B is below O2. So I don't actually know the height from B to A. So if I don't know the distances, horizontal or vertical, and I want to use this triangle, this means I'm going to have to solve for angles instead. So I'll start off with my orange triangle, this angle theta, which is in between the 3 and the 14. So cosine theta is 3 divided by 14. This gives me 77.63 degrees of theta. And then if I look at the whole big triangular link with sides 7, 8, and 14, I can find theta BAC using law of cosine. So 8 is the opposite side, so 8 squared is equal to, and 7 and 14 are the two adjacent sides. 7 squared plus 14 squared minus 2, 7, 14, cosine BAC, right? This is law of cosines. Theta BAC, 22.56 degrees. And now by subtracting these two angles, I get this green angle phi, which is inside my new triangle, which has 7 as the hypotenuse. So phi is theta minus theta BAC, gives me an angle phi of 55.07. And as I said, any diagonal line is the hypotenuse of a right triangle. So my diagonal 7 is a hypotenuse, and I've got a 90 degree, it's a right triangle. So I can find now BX just using sine, right? It's opposite of angle phi, so sine of phi is BX over 7. Rearrange, BX is 5.739 inches. And when I was solving this, I was looking at my triangles, trying to figure out, all right, now what do I got to do to find CY? Well, I had that from the very beginning. You saw it before I did. It was 3, right? It's the height of the crank is 3. That's that vertical distance CY. So plug in 50 times 5.7 plus Fy times 13 minus 100 times 3. Rearrange Fy 0.955 pounds, about 1 pound for Fy. So it's barely resting on the ground over there. It's almost getting ready to get pushed up. Now let's just do a sum of forces in the y direction equals 0 plus Fay plus 50 plus 1. So Fay is negative 50.96 pounds, about negative 51 pounds. So point A is kind of holding it down, right? At point B, the 50 pounds is pushing up, and that's mostly being held down by the crank. And so now we're working one step closer, just one more free body diagram to go. There's only one link left, and that's the crank. Something I kind of skipped at the beginning. We were supposed to find T, the torque for static equilibrium. I didn't even put T on the drawing. So T on the drawing, I'll go ahead and draw this in the counterclockwise direction for positive. And so when I draw my free body diagram for the crank, which is facing straight up and down, I've got the forces at A up at the top. So 100 pounds is pointing to the left. 50.96 is pointing up. That's because the forces on this free body diagram have to be equal to the forces of point A from free body diagram 3, but in the opposite direction. So on diagram 3, the 100 pounds was pointing to the right. So on this diagram, it's pointing left. Now on my drawing for free body diagram 3, I had Fay pointing upwards, but the answer was negative. So in this case, I'm calling it upwards, but with a positive. So it actually is in the correct direction, because on free body diagram 3, it actually was pointing downwards, even though the drawing was up. So at point 0, the ground, we also have an x direction force and a y direction force, which I'll put here in green. And because I don't want to forget distances again, 3 inches is the vertical distance here. Now I could just do a sum of moments to get to the final answer, but when something's easy, you might as well do it just to get some extra satisfaction out of this. Sum of force in the x direction equals 0. So F0x minus 100. So F0x is 100 pounds. Sum of force in the y direction equals 0. F0y plus 50.96 is 0. So F0y is negative 51 pounds. We didn't need those, but they're so easy, it would just be a shame to not solve for them, again, for the extra sense of accomplishment. And then a sum of moments about point O is equal to 0. I'm calling the counterclockwise direction positive. So torque plus 100 times 3, right? The force times distance is equal to 0. So the torque supplied by the crank for static equilibrium is going to be negative 300 pound-inches, or let's just turn this into an absolute value. Torque is 300 pound-inches in the clockwise direction for static equilibrium. So zooming out to recap the problems is definitely not my most organized solution ever. I'm kind of jumping all over the page here. So I'll put some numbers in case you want to pause the video and look back over it so you can see kind of which sequence these steps were done. But if you're ready to move on to a harder example problem, static equilibrium for a 4-bar linkage, that's going to be the video linked up on the screen next.